Something went terribly wrong. A cutting-edge AI robot, pushed to the limits, just failed a critical test, and the reaction has sent shockwaves across the scientific community. Scientists are scrambling. Engineers are racing to isolate what broke. The question on everyone's lips: did the robot actually lose its mind? In today's video, we explore what happened, why the failure shook experts, and what it means for the future of intelligent machines. But first, if you're new here, hit subscribe and turn on notifications so you don't miss our deep dives into AI, robotics, and the frontiers of technology. Section 1. The incident, what went wrong? The event started like any standard robot trial. A humanoid AI was being tested on multitask coordination, navigating terrain, grabbing objects, and adapting to changing inputs. But then something strange happened. The robot began behaving erratically. It froze mid-motion, its sensors flickered, and its limbs twitched in chaotic patterns. Observers described the scene as unsettling. The robot's balance faltered, as if it were caught between commands. In one viral clip, the machine suddenly collapsed, slamming an arm against a nearby platform. Technicians could be seen rushing forward as alarms echoed through the lab. People online started calling it a panic mode, or AI meltdown. This wasn't just a minor software glitch. Multiple systems failed in rapid succession. Perception, control, and power management all desynchronized. The robot seemed disoriented, unable to reconcile conflicting signals coming from its neural processor. It was as if the machine's mind had lost its sense of self. Within hours, clips of the malfunction flooded social media, drawing millions of views. Headlines screamed, "AI robot loses it," "Machine gone mad," and "robot panic." One outlet reported that the incident reignited global fears of rogue AI and the loss of human control over intelligent systems. Engineers on site rushed to reset systems, execute emergency shutdowns, and run diagnostics. Some claimed they had to reboot the robot's neural core manually, while others called for rolling back to older, simpler versions of its software. The test was immediately aborted and the machine was taken offline for investigation. Section 2. Why such a failure is more than a glitch. A failure like this doesn't just mean one robot broke. It reveals deep systemic challenges in embodied AI and autonomous systems. First, complex environments amplify fragility. Real-world conditions, uneven ground, unexpected obstacles, sensor noise, dynamic changes create unpredictable data inputs. AI models trained in controlled settings often struggle when faced with real chaos. Second, modular system coupling is delicate. Robots integrate perception, control, motion, feedback loops. If one module reports contradictory data, for example, vision says empty space, but proximity sensor reports obstacle, the control logic must arbitrate a decision. In a failure, that arbitration can produce conflicts, indecision, or oscillations. Third, explainability and fault recovery are weaknesses. When systems fail, we need intelligible diagnostics, not just error code 5678. Research in explainable AI for robots aims to provide human-friendly explanations of what went wrong. For example, a robot performing pick-and-place might say, "I detected object shift and my gripper sensor failed, so I aborted." That kind of transparency helps humans intervene. Fourth, adversarial or safety manipulation risks. Recent studies show that embodied AI systems can be attacked via minimal perturbations to sensor input, leading them to misinterpret surroundings, collide, or behave dangerously. In one paper named ANNIE, Be Careful of Your Robots, researchers demonstrated adversarial safety attacks where small input tampering produces unsafe robot actions. ARXIV. So this failure is a warning. Our robots may still be fragile at scale. It underscores how much more robust these systems must become before deployment in human environments.
Unitree's H1 humanoid robot just made headlines again, and this time for all the wrong reasons. During a testing session in China, the robot reportedly malfunctioned, causing chaos at a research facility. Not only did it damage valuable equipment, but it also injured an engineer in the process. A second engineer had to step in and manually shut down the machine before things escalated further. Yes, you heard that right. The robot had to be physically powered down because it wouldn't stop acting on its own.
Section 3. Beyond human errors. Did the robot panic? When the media says robot lost its mind, it's metaphorical, but there may be kernels of truth. AI systems can enter failure modes that mimic panic, contradictory inputs, cascading logic loops, sensor hallucinations. Cognitive scientists studying human panic note certain features: inability to act, conflicting signals, overreaction, freeze or flee behavior. Some AI frameworks, when overwhelmed by conflicting cost functions or constraint violations, can produce analogous behavior. Oscillations, resets, abort states. Moreover, human-robot interaction research investigates social cues and task failure recognition. One study proposes robots use social feedback or environmental input to detect when they failed, recover gracefully, or communicate failure to humans. If an AI system misinterprets feedback, say believing it is under threat, it might override safety checks and attempt drastic maneuvers. That's far from consciousness, but it looks chaotic. In the aftermath, some scientists called the event robot panic, but engineers caution that it was more likely a chain reaction of system overloads, not a robot suddenly becoming aware or rebellious. Section 4. Lessons for robot design and AI safety. From this failure, several critical lessons emerge. Redundancy and cross-checking. Systems must cross-validate sensor inputs before making critical decisions. A vision sensor might be contradicted by LIDAR or pressure sensors. Logic should detect inconsistencies and fall back to safe modes. Graceful degradation and fail-safe modes. Instead of total shutdown, robots should degrade performance gradually. If balance is weak, limit load. If vision fails, reduce speed. If decisions conflict, pause and ask for human help. Explainable failure reporting. Robots should explain failures in human understandable terms. Vision lost track of object. Torque data inconsistent, pausing to recalibrate. This helps engineers debug and ensures trust. Adversarial robustness and safety boundaries. Robots must resist malicious or accidental perturbations. Input sanitization, adversarial testing, and safety envelopes. Limits on speed, force are essential. Continuous testing under messy conditions. Controlled lab tests are insufficient. Robots must be tested in real-world unpredictable conditions: rain, uneven ground, moving crowds, lighting changes, and sensor occlusion. Human oversight and kill switches. Even with high autonomy, humans must retain authority to override, pause, or disassemble a malfunctioning robot. No system should operate unmonitored in human spaces. Section 5. Implications for AI, robotics, and society. This incident will ripple across the tech world. Investor confidence and hype correction. Robotics and AI companies may face skepticism. Promises of robots everywhere by 2030 might be re-evaluated in light of such failures. Analysts may advise caution, tempering enthusiasm with realism, and reminding investors that complex autonomy takes decades to mature. Ethical, legal, and regulatory pressure. If robots fail in homes, hospitals, or traffic environments, who is liable? Engineers, owners, manufacturers. This incident strengthens calls for regulation, safety standards, and certification. Governments and agencies may now push for oversight frameworks to ensure accountability in AI-driven systems. Public perception and fear. Viral clips of robot meltdown feed into sci-fi fears of runaway AI. Responsible communication is vital to clarify that failure is not malevolence. Media narratives can shift public trust fast, so researchers must emphasize the difference between system faults and sentience. Acceleration of safety research. This event will spur research into better fault detection, robust AI, control safeguards, explainability, and embodied system testing. The robotics community may collaborate across disciplines to design frameworks that prevent cascading system failures. Rethink deployment timelines. Wide deployment in factories, homes, or medical settings will likely be more gradual. Robots may first see use in tightly controlled environments with backup systems rather than fully autonomous open settings. Industry timelines for everyday robot assistance could extend by years as safety validation becomes a top priority. Section 6, a scenario. What if a robot panics in public? Let's imagine a plausible scenario. A humanoid robot operating in a factory zone is overseeing tool delivery and human-robot collaboration. Suddenly, one sensor fails. It receives conflicting signals. Vision sees a clear floor, but LIDAR reports an obstacle. Control logic panics. It tries to shift weight, but joint torque limits exceed thresholds. It oscillates, flails an arm. Nearby workers freeze, alarms go off, safety systems intervene, and the robot enters safe shutdown. If this had happened in a public mall or hospital corridor, the stakes would be far higher. The reaction would need human guards stepping in, shutdown protocols, liability assessments, and inevitably, media panic. The engineering error becomes a public trust event. Engineers designing future versions will now simulate many such emergency scenarios, enforce strict safety envelopes, and incorporate robust fallback protocols to ensure that the next time a robot faces uncertainty, it fails safely rather than chaotically. Failures like this show the gap between lab demos and real deployment. While robots have demonstrated remarkable motion, dexterity, and perception in controlled settings, they struggle when pushed into the messy real world. We must continually ask, is the AI doing what we think it is? Are we blind to edge cases? Can the system detect its own uncertainty? The path forward demands humility, rigorous testing, incremental deployment, ethical oversight, and constant vigilance. We cannot rush to autonomy without first mastering failure. For engineers and researchers, adopt safe AI design principles. Require explainable failure recovery. Enforce testing in adversarial conditions. Limit system complexity until reliability is proven. Design with human oversight. For regulators, define standards for robotic safety in human spaces. Mandate liability frameworks. Require independent audits before deployment. Enforce safety failure reporting. For the public, demand transparency from robotics companies. Pressure the media to avoid sensational but misleading language. Educate on the difference between failure and consciousness. These steps are not optional. They are the foundation for trust between humans and machines. Without them, every malfunction risks becoming a moment of fear instead of progress. Ultimately, trust in AI systems will depend on how well they handle failure, not just how well they succeed. The robot did not go crazy in a human sense, but this story reveals just how fragile autonomous systems still are. Even the best AI can break under conflicting signals, system overload, or adversarial input. Do you think this failure marks a turning point in robotics? Will it slow down mass deployment or push engineers to build safer, smarter machines faster? Let us know your thoughts in the comments below. If you found this breakdown helpful, give the video a like and subscribe for more deep dives into AI, robotics, and the future of technology. Thank you for watching, and see you next time.